Let's try the bumper car problem together. Nick Nolte has a mass of 70 kilograms, and he's driving forward in a bumper car with a velocity of 6 meters per second. He angrily crashes head-on into a kid driver. The kid only has a mass of 28 kilograms. The kid was moving at a velocity of 4 meters per second directly at him. So Nick Nolte and the kid are going opposite directions. Nick's going forward, the kid's going backwards. If each bumper car has a mass of 150 kilograms and Nick Nolte bounces back at 1 meter per second, at what velocity does the kid bounce back? Remember, since Nick was going forward, he bounces backwards. Since the kid was originally going backwards, he's going to bounce forward, since we have to have one direction in a horizontal direction, either forward or backwards. The key to a good collision problem is all about the organization of your work. We need to look at the momentum before and after. The total momentum before is equal to the total momentum after. That means the total momentum of all objects involved before has the same momentum as all objects after. Let's start filling in the information we know. There's two objects in this case. There's one bumper car with Nick Nolte. The other bumper car has a kid in it. They do not combine, so this is an elastic collision. They bounce off each other. We start with two objects, we end with two objects. If we only started with one or ended with one, that would change how we organize our work. So I need a column of mass, velocity, and momentum for each object and a total momentum for each side of the problem. Take a moment to set up your work just like this. Pause the video and restart it once you've completed this task. We can start filling in the given information once we have a place to organize it. I want to find the mass of Nick Nolte and his velocity. Both pieces of information are given to me. So to find his mass, I have that the bumper car weighs 150 kilograms and he has a mass of 70 kilograms. So I need to add those together. The object that's moving is 70 plus 150 kilograms to give me a total mass of 220 kilograms. Because there's a potential for a lot of little calculations in a problem like this, it helps to label what you're calculating each time. In this case, I know I'm finding Nick Nolte's mass. I had to add the bumper car to his personal mass. Once I've found his total mass, I'm going to plug that into the mass section of his column, his mass, velocity, and momentum. The velocity was a given piece of information. He's moving at a velocity of 6 meters per second forward, so that's positive 6 meters per second. I now know two of the three givens that I need in order to find momentum. If you have the momentum and the velocity, you can find the mass. You have the mass and the momentum, you can find the velocity. As long as you have two in that column, you can always find the third. I'm going to do the same thing with the kid's mass. The kid has a mass of 28 kilograms. The bumper car has a mass of 150 kilograms. So I'm going to add them together. 28 plus 150 equals 178 kilograms. Make sure that you include your unit every time. Not only is it best practice for any science class, but it helps you double check. This is the kid's mass. Mass is in kilograms. This is how you know you have the right variable in the right place. The kid's velocity was given to us as well. If Nick Nolte's moving forward at 6 meters per second, this kid is moving backwards. If he's going opposite of the direction of forward, he has to be going backwards. We always assign forward as positive, backwards as negative. We would also assign right as positive. Right's going to represent forward if we're drawing a problem out. Left is going to represent backwards or negative velocity. For both Nick Nolte and the kid, we have the mass and velocity of the before. So I need to multiply those together to find the momentum of each individual object. I'm going to take Nick Nolte's mass and velocity and multiply them together. The momentum formula is P equals m times v. I'm going to replace those variables with parentheses. M, in this case, is 220 kilograms. V, the velocity, is 6, positive 6, because he's going forward. This takes a little calculator moment. You may not know this particular product off the top of your head. 220 times 6 in your calculator is going to give you 1,320 kilogram meters per second. Remember, the unit for momentum is kilograms meters per second. Because it's the product of mass and velocity, the unit is the product of the unit for mass and the unit for velocity. So kilograms times meters per second. I can do the exact same thing with the kid's mass and velocity. I'm going to take his mass times his velocity. Remember, it's -4 because he's going backwards. It has to be -4. Multiply those together, quick calculator moment. It's going to give you -712 kilogram meters per second. Every time I calculate a value, I'm going to plug it right back into my table so it's all correctly organized. Notice that -712 is my answer, not 712. Be careful when you're deciding on the positive or negative related to velocity. Be careful when you carry down those negatives into a calculation. Be careful when you multiply positives times negatives or negatives times negatives. All of this matters. All of this changes because negatives have a bigger purpose in physics. Negatives tell us our direction. Notice in my work below, I labeled exactly what every calculation is. This is good practice. It helps you remember what you calculated for each step. Otherwise, you just have a mass of numbers. It's hard to double check what you've done, or it's hard to look back and understand what you've done to help you with other problems in the future. I need to have mass, velocity, and momentum for each object, and I also have to have a total momentum. So to find the total momentum, I add them up. Total is always a good keyword in word problems for addition. So 1,320 and -712 kilogram meters per second. That's the total amount of momentum that we're looking at. One is positive momentum going forward. One is negative momentum going backwards. Remember, the negative just means it's going backwards. Add those together, so the total momentum, 1,320 plus -712, gives me 608 kilogram meters per second. This is my momentum before the collision, before the two bumper cars bumped into each other. I'm going to write it directly into my table. So my total momentum before is 608 kilograms. Law of conservation of momentum states that momentum before, total momentum of all objects before a collision, equals total momentum of all objects after a collision. So I'm going to bring 608 kilogram meters per second over to my total momentum for the after. My mass does not change unless the kid got thrown out of the bumper car. The mass of both objects will remain exactly the same, so I can bring those over as well. Now we can finally start to get to our final answer. The question's asking, what velocity does the kid bounce back at? If you're ever concerned about what the question's asking, answer everything. If you can solve for the kid's velocity, the kid's momentum, Nick Nolte's momentum, and Nick Nolte's velocity, if you can solve for all those things, fill it in. Then double check the question to see if you've answered it already. Solving for the kid's velocity is not as easy as one step. We have to kind of get there by following clues, looking at what we have. There's not a 1, 2, 3 here. You need to use the information that's in front of you. So I was given that after the collision, Nick Nolte bounces back at 1 meter per second. I need to think logically about this. He started going forward. If he gets bounced back, now he's going backwards. So that means that Nick Nolte has a momentum of -1 meters per second. Be very careful. Always determine whether your velocity is going to be positive or negative. I need to then find what I do next. You have to look at the information that you have in front of you. Look at your table. You can only calculate a column if you have two of the given pieces of information. You either have to have mass and velocity, momentum and velocity, mass and momentum. You have to have two of those to find the third. In this case, in Nick Nolte's column for after, we have 220 kilograms and -1 meters per second. So I can calculate Nolte's momentum. Label it every time. It will really help you keep all these little calculations organized. We're not dealing with things like the kinematics where we have one big calculation. We have a lot of little calculations here. So I'm going to take his mass times his velocity. So I replace m and v with parentheses. So I can plug 220 in. I can plug -1 in. When I multiply those together, it's a little calculator moment. Always remember, you have a negative velocity, so you have to have a negative momentum. So when I take positive 220 times -1, I get -220 kilogram meters per second. Remember, the unit for momentum is kilogram meters per second. Every time that you get an answer or calculate an answer, with these little calculations below, it goes directly into the table. At this point, we have Nick Nolte's velocity, Nick Nolte's momentum, but we don't have the kid's velocity. That's what we're solving for. There's not a way to directly go to it, because if you look at the kid's column, we only have one given. We need at least two to find the third. However, I do know the total momentum of both objects. The total momentum is calculated by adding the momentum of each individual object. So if I know one of the object's momentums and the total momentum, I can find the other object's individual momentum. So I'm going to find the kid's momentum. Take the time to label it out because there's a lot of little calculations here. If it helps, write out that the total momentum equals Nolte's momentum plus the kid's momentum. So I have a total momentum of 608. I got that by adding 1,320 plus -712 at the beginning of the problem. I got -220 by multiplying 220 kilograms times -1 meters per second. And I don't know the kid's momentum. Treat this like a one-step equation. What's happening to the variable, in this case the momentum of the kid, I'm adding -220, or I'm subtracting 220. To undo subtraction, I'm going to add 220 to both sides. That's going to give me 828 kilogram meters per second. That's the kid's momentum. Always include, or every time you get a calculation, include that value directly back into the table. You can double check this by taking 828 plus -220, the individual momentums of Nick Nolte in his bumper car and the kid in the bumper car. Add those together, you get 608. Now that I have two values in the kid's column, I can calculate the third. So if I want to find the kid's velocity, I'm going to use the same formula, my momentum formula. I'm going to replace the variables. I have P, I have the kid's momentum. I have the mass of the kid in his bumper car, 178. This is a one-step equation. So what's happening to my variable? I'm multiplying by 178. To solve it, I'm going to divide both sides by 178. That's going to give me 4.65 meters per second. Plug that right back into the problem, and that is our answer. There are a lot of little equations involved, but it's all the same equation. It's only three variables. P, which is momentum, M, which is mass, V, which is velocity. If you need help remembering it, you can remember it as MVP, mass times velocity equals momentum. Now, individually or with a partner, you can start on the remaining three problems. These are your practice problems. If you finish early, you can go ahead and start on your summative assessment preview. It's going to look exactly like your summative assessment that's going to take place tomorrow.